Hi guys, today we will learn supervised contrastive learning versus softmax classification. This notebook demonstrates and compares two approaches to supervised classification: standard softmax classification using cross entropy loss and supervised contrastive learning followed by a linear classifier. So first we're importing our libraries, then we're doing data preparation. Then we're importing libraries and we're reshaping if needed. You can see the image. Then supervised contrastive loss implementation. In this, we are making a class named supervised contrastive loss. Then model architecture. In this, we are defining a function named create encoder, which is peer encoder architecture and projection head for contrastive learning. And contrastive learning model in this, we are making a class, defining a function, create and compile models, training the contrastive model. And this, we are creating custom training loop for better control. Then extract encoder for classification, add classifier head, as you can see on the output. Then training softmax baseline. In this, we are making classifier softmax. Then we are training and evaluating classifier. So we are training the classifier with contrast to pre-trained encoder, evaluate both models, and embedding visualization by with TSA. We are printing the simplest approach, contrastive model, softmax model, apply TSNE, visualization of future embeddings. So we are plotting various graphs here, such as TSNE visualization, contrastive learning, TSNE visualization, standard softmax. Then we will move on to auto transfer learning. Uh, Here the key objective is load YML, AMNet, feature restriction, fine tuning, compare both approaches. For that, we're importing all the libraries. In audio data preparation, create mock audio data for demonstration, create 5 different classes, generate radio, random audio, speech like fluctuation, musical tones, natural sounds, urban sound normalize. Mnet feature extractions. So load Mnet get the class, extract features, then feature extraction approach. In this, we're building a classifier using Mnet. Split data, skill features, and train the model. Uh, then we are fine tuning the model, compile with lower learnings, upon comparison, extraction versus fine tuning. Then there's evaluating feature extraction, then evaluate fine-tune model, visualize training history, plot of the graph, show the model accuracy comparison and model loss comparison. Then classification analysis. So we are visualizing the auto classification results, get prediction, convert to class labels, confusion metrics, fine-tuning, classification reports. We can see this is confusion metrics of feature extraction and fine tuning, then inference and visualization. And in this, we're demonstrating prediction on new audio samples, rest on some samples, visualize spectrogram of a sample. After that, we will move on to image classification with transfer learning. In this, we will import all the libraries for data preparation. You can see the output, data augmentation and data sets, implement data augmentation, create data set, create augmented data set, visualize it, all that stuff. You can see the output augmented images, then feature extraction with efficient net P of P0. So load efficient net P0 for feature extraction, freeze the base model, build the feature extraction model, and print model summary. As you can see the summary, then training the model, evaluate, build, fine tune model, initialize training, and final results in comparison. Fine tuning phase 2. As you can see, increase the top layers, final evaluation, accuracy comparison, final comparison, bar chart, and print summary. So this is the output. Then we will move on to video action definition transfer learning, import all the libraries, video data preparation, then create a mock video data set with reordered classes, then generate mock data set with feature extraction with i3D. In this, we are loading pre-trained video model from TensorFlow Hub, get the model signatures, i3D expects videos in a specific format, extract features, then extract features, and train video classifier. For this, we are splitting the data for training and splitting the data for text scale features, build a simple classifier, train the classifier, video classification results. So we will let and visualize results evaluate on test set, plot confusion matrix and classification report. This is the confusion matrix and this is the report based on jumping, sitting, walking, standing, running, video prediction visualization. So predictions, make prediction, plot training, accuracy plot. These are all the plots, frame 0 to frame 15. In jumping, sitting, running, everywhere, everything. And this is the graph model accuracy and model loss. Then we will move on to transfer learning quick transfer using TensorFlow Hub. So in this, we'll first install all the libraries, then we'll import them. Then we load the flowers dataset, pre-process the dataset, visualize the dataset. As you can see, these are all the sample images in 2x to grade sunflowers, roses, tulips. Then create a training pipeline. Once we log in install required libraries, which is Keras. We create a simple transfer learning model, freeze the base model, and compile the model summary, train the model, and then we will move on to zero shot transfer learning, explore zero shot classification with clip. So set up, install various libraries, import modules, and select compute device. Load clip model, create text image. This is the image platform zero shot classification. Visualize zero shot results. As you can see, the visualization of clip zero shot prediction, purple object, vibrant red and shiny surface, artistic background, glossy item. There's zero shot on multiple colors. As you can see, different color, purple, orange, shine, lime. Then we will move on to 3D event classification of CT scans using deep learning. For data generation, first we'll import all the libraries, ensure consistent results, create synthetic 3D volumes, and split into training and validation sets. So the model architecture, first we'll build 3D CNN model, first 3D convolution block, second 3D, third 3D and fully continuous, then compile model, build and train model. At last we'll print the summary. Then model evaluation and visualization. So in this, we will first evaluate model and plot the various graphs, visualizations. As you can see, model accuracy, model loss, slice 0 to slice 31st. Then final evaluation and model shaping. In this, we'll calculate classification matrix, print classification report, plot matrix, confusion matrix, save model and conclusion. Here is classification report based on precision, recall, F1 score, support, confusion matrix, then conclusion. Uh, Now we will move on to CIFAR and classification and transfer learning models. In this, we'll import all the required libraries, load the dataset, normalize it, convert the class labels, randomly select as samples, then image preprocessing for transfer learning will first create a data set, create transfer learning data set, visualize a few examples and plot the graph. As you can see, visualize various such as horse, ship, frog, bird, automobile. An efficient net transfer learning model. In this, we will use Keras to build in efficient net implementation, freeze the model, create the new model, preprocess, all that stuff, compile, train, evaluate the model. Then with this will be transfer model implementation. In this implement bit for comparison, create model, new model, freeze model, compile all the same stuff, evaluate the model. Uh, then convex implementation. Seeing this a simpler convex inspired implementation initial step block, and then we'll compile the model, train it, and evaluate it. Model comparison. So here we'll visualize different model, compare it. As you can see, model comparison on the data set, then best performing model and all the other visualizations. Then we will move on to fashion and risk classification with transfer learning models. Here, as you can see, we are first importing our libraries, and as usual, we set seed for reproducible experiments, load fashion, and dataset from Keras. Same stuff always. Then image post processing for transfer learning. Um, then we'll create transfer learning dataset, visualize a few examples of data or datasets. Then efficient net transfer learning model. Use Keras to build an efficient net implementation. Then big transfer model implementation. Implement it, compile the model, evaluate it, train it, come next. Same stuff as we did before. Model comparison, visualization, all the visualization will be there. Um, yeah, then we'll move on to combination classification with transfer learning models. First, import all the libraries, same stuff, image preprocessing, transfer learning. These are all the visualization level 1, level 2, level 3 to level 6, and um, transfer efficient net transfer learning model. Create the new model, preprocess, compare it, train it, evaluate it, same stuff. With model implementation, create it, train it, evaluate the model for next implementation, simplified convex initial step, create it, train it, evaluate it, and model comparison, all the visualization of the model. Then X-ray pneumonia classification with the custom built connect. Here what we are to do is first we'll download data set from Kaggle, unzip it, and then we'll import all the libraries, dataset path, then image processing, build concept model, train the model, and print summary. This is also summary, model evaluation and visualization. So evaluate plot accuracy. This is all the plot, model accuracy, and model loss. This is the output. True, normal, all the stuff. Then model saving. Save the model, load the model, display the image with prediction, model evaluation and conclusion. So, and this will print classification report and conclusion. This is the classification report, normal pneumonia accuracy. Then this is the conclusion. We have successfully built and trained a ConNet model for X-ray pneumonia classification and achieved 79.17 accuracy on the test set. So this was computer vision assignment. Thank you so much for watching.